I'm going to try to just go through this relatively quickly, and if you have any questions, let me know. But if we take a pyramid and we were to slice it, could make a whole bunch of slices. Then each one of these slices we can think of, right? We can approximate it with a rectangle. Or instead of a rectangle, we can think of it as a prism. Each one of these is not a pyramid, but we can approximate it with a prism. So all of the sides would be vertical for our approximation. All right, so that gives us the idea anyway. So we take a pyramid, slice it. So we slice the pyramid into slabs, as we see here. Then we can let x be the distance from the apex to a given slab. Okay, so if we are looking at this with x being the distance from the apex to a slab, of course, the apex is the top of the pyramid, and then if we were to choose a random slab, this distance would be x. Okay. Also, we would have this distance here, we can think of not as star x. That's not what I want. Delta x. So the slab, the thickness of the slab is delta x. So that way, when we think of if the distance is from the apex to one of the slabs, then we're going to integrate either from the apex to the base or the base to the apex, whichever way you want to think about that. But then we need a way to say, all right, what are our increments of change here? Well, our increments of change are how much we're changing in x, so that's the thickness of a slab. So we can take this, and what we have, well, actually here, let me add something here a second. I can erase, get rid of this here, and go back to red for a moment. If the overall height is h, and we can find a way of expressing the volume of these slabs. So the shape of each slab is similar to the base. Okay, so if we consider the base, then as we move upwards, each slab is going to be the same shape. They're just getting smaller and smaller and smaller as we move up. So the shape of each slab is similar to the base with a scale factor of SF is equal to x over h. So however far away we are, as we get closer, the distance closer to the apex, the x value is smaller and the h stays the same. So as we get closer to the apex, of course, the scale factor is smaller and smaller. So we have something that's smaller and smaller compared to the base. The area of each slab is the area factor times the area of the base, which would be x over h squared, because the area factor is the scale factor squared, times a. All right, so with that, the slab is, each slab has a thickness of delta x, as we said earlier. So then the volume of each slab, right, which are prisms, is, now each one of these slabs represents the change in volume, because as we add more, we're getting a change in volume. So it represents the change in volume, which is the base times the height, area of the base times the height, so x over h squared times a, the area of the base times the height of the slab. Thus, the volume can be given by the integral of the differential, which is the integral of x over n squared times the area dx. But I have an n squared that I can pull out, 1 over n squared, and the area I can pull out. So this is area over, or sorry, h squared over h squared times the integral of x squared dx. And of course, that would simply be 1/3. In this case, this is a definite integral, so we would be integrating from 0 to h, 0 to h, the height of the pyramid. And so that would be a divided by h squared times the evaluation, 1/3 h, or 1/3 x cubed, evaluated from 0 to h. And because I'm limited on room, we'll just say that evaluates to, skipping a step here, 1/3 a times h. So when I plug in the h, I would end up with 1/3 h cubed. The h's would cancel, and you'd have a times 1/3 h, which is exactly that. When you plug in 0, you'd have 0, distribute 0. So it's just that. And that's the end of the proof, right? We found the volume to be, as was suggested, 1/3 area of the base times the height.